section of that. So we're jumping all the way back to 1-4, and you'll start off with this goal of using an arithmetic sequence and how you represent and find the terms and the sums. As you do, I really want you to connect back to Math 1 when you worked with now and next. And so recursion is a way of thinking. Oftentimes we talk about recursion and iteration when we're talking about programming and doing loops and working backwards. And so as you go, there is a helpful Khan Academy video, but one thing to really keep in mind is notation. How we write things in math and rewrite things in math. And so as you're working through this notation, if you want to go to now and next in your brain, that sometimes might help you. So with the critique and reason, we have Yumiko and Hugo, and they're looking at this table, and you have to decide who is correct. One thing that I really love to do is called arrow roads. So as I go from 1 to 5, I'm adding 4. As I go from 5 to 9, I'm adding 4. And sometimes you're going to see that the book didn't give you a table, it's just giving you the sequence. You can always put it into a table, and I would recommend that. So we can see that the first difference here is very consistent, and so we've got Yumiko and Hugo, and they're arguing. Yumiko writes 1 plus 4 equals 5. Then f of 1 plus 4, that would be 5 plus 4 equals 9. And then you've got the previous value plus 4, so that previous value was 9, plus 4 equals 13. And so what you're seeing is a now plus 4 equals next. Notation-wise, let me scroll down a little bit if it will cooperate. When you see the subscript, and you're seeing this a subscript n minus 1, that's saying the previous value. The now plus 4 equals the next. So when you see n and n minus 1, you're working between. So if we're starting here I'm going to go back one. If we were to jump in anywhere, because that's part of being able to use this recursion is to say, okay, well, what if I started at number 68? And so being able to go back and forth between a recursive formula and an explicit formula, that's kind of the goals of this. So if I started at 2 and I went, n was 2, that would be my next, and the previous one would be 2 minus 1, and so we would be at an input of 1. As you go through, you'll look and you'll say, okay, well, if you started at the 100th one, which would be a more useful way of thinking about it? Yumiko's or Hugo's? Into example 1, you're looking at the sequence, and when we're talking about natural numbers, we've talked about number sets in the past where we have like our counting numbers. Those are our natural numbers. And then we have whole numbers and integers and beyond that. So first thing is to create a table, and they've done that for you. And if you're keeping track of vocabulary, which I would highly, highly, highly recommend, you've got a lot of words in this section, but the arithmetic sequence is a sequence with a constant difference between consecutive terms. So like I was showing you in the Victor and the Hugo and the Yumiko one, we're looking at the difference between consecutive, meaning in a row, y values. And so in this table, it's 5. That's the common difference. And know that terminology because it is going to come back and they're going to ask you about the common difference. When you get to part B of example 1, this is where you start to see that notation. And so as you're looking, you're thinking about function notation. So f of 1 is 3 and f of 2. So if you think about numbering the terms, this is our first term, our second term, our third term, our fourth term, and so on. And so this n minus 1 right here, Let me highlight that. That's going to be our previous term and what's happening in it. So this is the recursive definition of an arithmetic sequence. Each term is defined by operations of the previous term. What did we do to now to get next? In this case, we're adding 5. So in this case, you see, in order to get our next term, what we're doing is we're adding 3 to our previous term. And so if we start, we always want to identify where we start. Anytime that we're working with a recursive nature, we really want to make sure we identify where we're starting. So we're starting with the first term. Remember that when you write a linear equation, you're starting at 0. So you're not starting at the first term, you're starting at like when you're on that y-axis. And so that's not the first term. This is going to be the one where x equals 1. So in this case, we've got our now plus 3 gives us our next. Our now plus 3 gives us our next. Our now plus 3 gives us our next. And I'm just going to go back 1 second here. Hopefully my computer will cooperate. And thank you for watching this video if you are watching. This is the recursive definition. And so as we're thinking about that, we're saying, okay, 4 is when n is 1. We're starting at 4. We take our previous term plus 3 for values that are greater than 1. In the triads, you're going to be decreasing. And so you probably have maybe done these, but we've got our now term minus 5. So when we start at 25, we're dropping 5 to 20. We're dropping 5 to 15. We're dropping 5 to 10. This is our recursive definition. Some of you have already seen like the equation for this rule, the explicit function, that linear function you already know. But in this, we're looking for the recursive. This one, you're looking and you're checking to see if this has that common difference. So 2 plus what gives you 4? That would be 2. 2 plus what gives you, or 4 plus what gives you 7? That would be 3. From 7 to 12, that's 5. And then we're only going by 1. So there is no common difference there. So it is not an arithmetic sequence. In order to find the explicit definition, we're going to say our starting term. So that's usually what we're given. And we're going to take our common difference times n minus 1. You're like, well, why are we doing this n minus 1? That's so that we can get to that y-intercept. Let me see again if my computer will cooperate. So in this pattern, we know that from our recursive definition, From our recursive definition, we know that we're starting at 3 and that we're taking our now and we're adding a half. So if we go ahead and label, we're like, okay, a sub 1 is 3. A sub 2 is 3 plus a half. To get our next value, we're going to take our a sub 2 plus a half. Well, our a sub 2 is 3 plus a half, so we're going to add another half. And so we're just going to continue adding a half. In order to do this explicit function, then we're going to start with 3. That's our a sub 1 from above. We're going to take our n minus 1 times a half. Now, if you're like, but what if we distribute this? So let's do a little more work right here. Just give my computer 1 second to catch up. You can check your phone, eat a bite of pizza, whatever you're up to. Okay, so I want to go right here and I want to distribute. So we have our 3 plus our common difference of 1/2, and when I distribute that, we're going to take that times our n. but we have to make sure we distribute here. So we're going to take off that 0.5. Oh my goodness. So you can't barely read that. Have another bite of pizza. Check your phone again. I'll see if I can get there for you. So we take off that 0.5. Now we're like, oh, that's 2.5 plus 0.5n. And so this is our a sub n. So this is our explicit definition, but now it's in simplest form. And so if you can't read my handwriting, this right here in the circle says 2.5 plus 0.5n. So these two definitions are representing the same sequence. This one here is in simplest form. And it's a linear equation. And so we're like, okay, if we were to track that pattern back, we know that we were starting with a sub 1. And so if we go back up, we would take off a half. We would take off a half and we would be at 2.5 for our a sub 0. Okay. Hopefully that made some good connections. Okay, so as we go, that was example 2. Please message me with questions always. In example 2 part B, you're going to, given the explicit definition, they're going to ask you to write the recursive. So we're pointing out those key parts. That is our a sub 1. This is our common difference. And so when we're looking, we're like, okay, we know the important stuff right here. And the rest of it is just writing it with that specific notation. You can check your work here. Again, there's the spot where we put our a sub 1 is right here. And so we can pull that right in to our definition down here. Our common difference is right here, so we put that right there. And then we do want to simplify. When you go into the practice and problem solving, you want to distribute that -2 and simplify and combine like terms. This is where it gets a little bit funner because now you're like, where am I ever going to use this? Zach Crawford, I'm talking to you. When you think about it, this is a movie theater, and so the high school auditorium has 18 seats in the first row, but 26 in the fifth. And so how can you use this information to help you find the explicit definition for the sequence? So we know our starting value, we know our number, and so we can plug those things in. And so we're going to write the general explicit formula. So we've got a sub n equals a sub 1 plus our common difference times our now, n minus 1. When we put in 26, 18, and 5, we then can simplify to 26 equals 18 plus 4d. And we can keep simplifying so that we can know our common difference. So now we can write the explicit formula for any row there with our common difference in mind. That allows us to find our 120th term. So we wouldn't want to really use the recursive definition to find the 120th term. That'd be so far. And so using the recursive to get to the explicit allows us to find that 120th.